Section 9.5 is geometric series. Our goal is to define geometric series and find their sums. On page 722, we have you can write any whole number that has the same digit in every place as the sum of the terms of a geometric sequence. For example, 4,444 is equal to 4 times 10 to the 0 power plus 4 times 10 to the first power plus 4 times 10 squared plus 4 times 10 cubed. You can write any rational number as an infinite repeating decimal. For example, 47 divided by 90 is equal to 0.5222, so on. Therefore, you can write any rational number as a number plus the sum of an infinite geometric sequence. For example, 0.5222, so on, is equal to 0.5 plus 2 times 0.1 squared plus 2 times 0.1 cubed plus 2 times 0.1 to the fourth, and so on. Just as with finite arithmetic series, you can find the sum of a finite geometric series using a formula. You need to know the first term, the number of terms, and the common ratio. On page 723, we have a geometric series is the sum of the terms of a geometric sequence. The sum S sub n of a finite geometric series, a sub 1 plus a sub 1 times r plus a sub 1 times r squared, plus all the way till we get a sub 1 times r to the n minus 1, where r does not equal 1, is S sub n equals a sub 1 times the quantity 1 minus r to the nth power divided by 1 minus r, where a sub 1 is the first term, r is the common ratio, and n is the number of terms. Example 1 says, what is the sum of the finite geometric series? For part A, we have 3 plus 6 plus 12 plus 24, all the way until we get to 3,072. At the top, I have the formula from the previous slide. Here we see that 3 is our first term, our second term is 6. 6 divided by 3 gives us 2, or the common ratio, r. Now to find the value of n, we can use the explicit formula for a geometric sequence and plug in our a sub 1 of 3, our common ratio of 2, and then we have 3 times 2 to the n minus 1 power will be 3,072. Our goal is to get n by itself, so we can start by dividing both sides by 3. 3,072 divided by 3 gives us 1,024, and 3 divided by 3 gives us 1, so we're left with 2 to the n minus 1 power. 1,024 can be rewritten as 2 to the 10th power, so now we have 2 to the 10th equals 2 to the n minus 1. 2 to the 10th and 2 to the n minus 1 have the same base of 2, so the exponents must match in order for the left side to equal the right side. Therefore, 10 must equal n minus 1. We can add 1 to both sides to get n equals 11. Now we have a sub 1, r, and n, so we can use our formula from the previous slide to find the sum of the first 11 terms. S sub n is equal to a sub 1 times 1 minus r to the nth power all over 1 minus r. Here we have n equals 11. Our first term was 3, and our ratio is 2. So we have S sub 11 equals 3 times 1 minus 2 to the 11th power all over 1 minus 2. 2 to the 11th power is 2,048, and 1 minus 2 is negative 1. So now we have 3 times negative 2,047 divided by negative 1 gives us 6,141. So the sum of the series is 6,141. Part B says, what is the sum of the finite geometric series 4 times 1/2 to the power of n from n equals 0 to n equals 20. Since we start at n equals 0, we can find our first term by plugging in 0 for n. 4 times 1/2 to the 0 power gives us 4 times 1, since anything to the 0 power other than 0 is 1. Therefore, we have 4 times 1 equals 4. So our first term, a sub 1, is 4. Our common ratio is right here, 1/2. And then to figure out how many terms we have, we know we start at 0 and go all the way to 20. So we actually have 21 terms. It starts at 0 instead of 1, so we have to add 0 in, which gives us 21 rather than just 20 terms. Now we can use the formula above to get S sub 21 equals our initial term 4 times 1 minus our common ratio 1/2 to the nth power, which is 21, all over 1 minus r, which again is 1/2. This gives us 4 times 1 minus 1/2 to the 21st power divided by 1/2, since 1 minus 1/2 is 1/2. We can simplify this a little bit. Since 4 divided by 1/2 gives us 8, we now have 8 times 1 minus 1/2 to the 21st power, and if you plug this into a calculator, you get about 8. Therefore, the sum of the series is about 8. The work for this problem is written out on the next few slides. And now I would like you to try number 1. Evaluate the sum of the finite geometric series, -5, -10, -20, -40, minus all the way till you get to 2,560.